me show you how to be a good breezy and change your predictions.
So first, folks, for those who really don't know about the zero-sum normal and the zero-sum constraint, really I recommend listening to Adrian's episode, because we go into details about why and how you would use that and the strength and the weaknesses. But the short version is you would use that mainly when you have, let's say, categorical covariates in your regression. So for instance, like in the Radon example that everybody knows from Andrew's paper, you have homes. And so if you have a global intercept in that model, for instance, which would be the mean of the homes, then if you partially pull the coefficients on the homes, you are going to have to use a zero-sum constraint on the parameters of the home. Otherwise, you have an over-parameterization because you're estimating two intercepts in a way. So you would have these parameter in there that's pm.zero-sum normal, dims equals home. But then my question to Sean, and that's because it's a question I often have, I often work on, whether for elections or other purposes, is like, what if you have, so homes here, we often call that groups, like if you use BRMS or BAMI, that's what they call that, their group, so that's one group. My question was, what if you have a new element of that group? So the group is known, and you've inferred the population parameters of that group, but you observe a new home. How do you handle that? Because then the zero-sum normal constraint is not, is not observed in the test set, because now the mean changes because there is a new element. So yeah, that's the context. And so apparently, Sean, you've done some homework about that, so thank you. And I'm also very curious to hear about what Adrian's thinking is about that. So yeah, first let's hear from you, Sean.
Yeah, okay, so the distribution, so okay, we take our zero sum and we say that if we assume normality, so it only works with normal, I think. Okay, good.
At least that's. I also only know how to do it with a normal. If it's not normal. Okay. So maybe, I don't know.
Maybe there's some clever ways to do it with something that's like normal-ish, but closed under some of the normal properties of like addition and all that. But anyway, like normally, right? Often when we do hierarchical models, we do have this like normal property of these like random effects and fixed effects and everything. So it's nice because of that. And when you look at the distribution of the zero sum and you estimate what that covariance matrix is, it's got this diagonal property, and then it has all the off diagonals have like a negative covariance. And what we can actually see from all of this is that using like I just like want to get into all the math, but I feel like if you're listening to this, it would be super annoying. So I'm just going to try to like say it in a general way, which is you can take the property and what you've estimated, and you can actually like back out what like the population like mean effect is, or the variance of the population mean. So the variance of your mu, your intercept, or your fixed effect in the zero sum case will be much smaller when you use a zero sum. Like the variance of that mu will be much smaller, all right, than if you just had a regular hierarchical model. Now, the really cool thing though is that with the zero sum thing, the estimates that you get on the mean of mu are actually typically much better often, and you get higher ESS and all these things. Like the HMC is able to sample from the zero sum often much easier than the non one. And so you can actually go back and you can get the population standard deviation, and you can generalize out, because we're going to know, we can back out like what the covariance and take those effects into account. And then we could say, oh, if we had a new group, this is how all of the other effects would change in the zero sum, because anyway, there's a way that you can like look at all the addition, like what you add to it, and then the new one, but it's just going to be based off the prior and what you've estimated from your sample. So it's not going to be like, maybe there's some clever way to include like some information about how large that group is or some other standard deviation effects. But right now I just like looked at it from, okay, if you use your posterior of what you have in your prior and then this information about the multivariate normal that's implied by the zero sum, then I think, yeah, you can do it. Which is very long-winded, but I don't know, Adrian. I want to hear maybe you have a cleaner way, because I like literally just worked on this for over the last day or two, and so it's a bit new in my mind.
Yeah, what I really is kind of oh, sorry. Yeah, go ahead.
Yeah, no, just Adrian, if you like, just to tell you guys, if you feel like you want to share your screen because it's going to be easier to explain, you can do that, right? Like, especially now. On the YouTube episodes, we had the video, so people, if they want, they can refer to that. So yeah, if that's helpful to your explanation at some point, sure, feel free to do that. You should be able to share your screen. And now, Adrian, yeah, back to you. So if I understood correctly, Sean, what you said, it's mainly, well, you cannot directly, of course, have information about that new home, for instance, but you learned about the population parameters, so you can use those in your predictions. And well, if you had better priors about that new home in particular, then definitely use those prior in conjunction with what you learned about the population, and that you can make a prediction based on that.
And how like the zero sum constraint, like how that manifests into the model, and it's almost like you're backing out that effect and then applying this new group, and then you can like reapply it, and then you could rederive everything.
Yeah, I think what cleared up my thinking around that a little bit was seeing what happens if kind of really distinguishing between effects relative to the population mean and effects relative to the sample mean. So if I have an infinite population of homes, or a population that I assume is infinite, and I have a sample of 50 homes from that population, then I can ask, is the radon level or whatever level 50% higher than the average among the homes that I observed, or is it 50% higher than the average of all the homes that there are? Kind of one is relative to the population, the other is relative to the sample. And if I don't use a zero-sum normal in my model, I can always compute both, right? I can just say, okay, I've got my posterior, and I can take the home-specific value and just subtract the mean of all the observed homes in that draw. Then I get back kind of the zero-sum effects kind of relative to the population of homes that are observed. So the relative to the sample of homes that are observed. And sometimes, kind of depending on the application, sometimes you might want to look at one, and sometimes you might want to look at the other, right? Maybe I'm interested in how much more radiation is there than the average home, or I might be interested in how much more radiation is there compared to the homes that I observed. Especially kind of if the population I'm looking at actually isn't infinite, like, I don't know, US states or something. It doesn't really make much sense to ask, is that value in that state higher than some infinite population of US states? I mean, there are only that many.
Yeah, I mean, actually, that just like that's a great. I love that, like the difference between the sample and the population. Yeah, if I think of alpha as like our random effect, and if you take the mean, and so that would be the random effect by group. So you might have k groups, whatever. If you take the mean of it in the zero sum case, that mean is going to be zero, right? Like, by construction. But in the case of just like a traditional hierarchical model, it will be non-zero, and you'll have some non-zero variant. And so I think like that is kind of the key, right? Like that, like you have, this average effect, and then, okay, we can use that to sort of back everything out. But it's actually really neat. And Alex, I just want to thank you for bringing that up at StanCon, because I think it is quite neat. I don't know. Do you guys have anything written up on this?
You're asking the wrong person for a nice written up. Unfortunately, I don't.
I know.
We did the bit of that.
We should write up.
Yeah.
But kind of
I mean,
to
yeah,
get
for
back to how you can then get back the population effects is kind of if you start with your model that counts everything relative to the population, so the infinite population of homes, then it turns out you can just distinguish that in the model itself. So you can take a normal distribution with mean mu and so some fixed mean, and you can just decompose that into a zero-sum normal and a normal distribution for the sample mean. So you have a scalar distribution that's the sample mean of the population, of the sample, not the population. And you have a zero-sum normal that tells you what's the distance to that sample mean. And then kind of if you write it down, then you have kind of a scalar value with a normal distribution, and you have plus the zero-sum normal plus the normal distribution from your intercept. And then you can marginalize intercept plus that thing. And then you can kind of turn a normal hierarchical model into just strictly a reparameterization of a zero-sum normal. And you can then kind of take the zero-sum normal and go back the other way and try to kind of undo the marginalization manually after sampling, which is really annoying to do. So I'm usually too bored, or not. I usually don't, to be honest, but it's definitely possible. And if you add more layers, it gets more involved. So less fun, but.
Yeah, it would be nice to have like an automatic way to just do this, because I mean the zero sum, it does, at least in my test, like it does sample often, almost like 95% of the time better than just like the regular hierarchical model. So you're going to get better estimates, and then when you do all the backing out, of course, like it translates to all of that.
Yeah, I would definitely really like to have a library that you can just tell, here my effects, code that as a zero-sum normal, but give me back a trace object that includes not just the zero-sum effects, but all the population effects as well. So you have access to both, and you can look at whatever you're actually interested in your application, but the sampler sees whatever's better for the sampler. So that would be really nice to have, but I don't think that exists at the moment.
No. And we started
next project for NumPy.
Yeah. And we started doing a bit of that, Adrian and I don't know, a year ago or something like that, where we have a proof of concept, but we
never cleaned it up, though.
We never cleaned that up. And also it's because like it gets, like if we want to put that into PyMC, it has to deal with all the different models people can have. And then if you have a lot of zero-sum normals in there, that's like really hard to track everything down. So I think the stuff we had was already quite complete in the sense that it was like main effect for A, main effect for B, and interaction of A and B, and then how do you recover the population means, because you have zero-sum normals everywhere in this model. But like people can make arbitrarily complicated model in PyMC, so then it's very hard to generalize. But yeah, that would definitely be a very, very valuable contribution. I know Luciano Pass did a lot of work on that with a client at PyMC Labs, but I don't know how generalizable that stuff is. So yeah, like that's something we should probably ask Luciano what he thinks about that.
Maybe we need 3 or 4 non-generalizable implementations, and then at some point we can extrapolate an actual implementation that works in at least most cases. But yeah, exactly. But for sure, it's the good thing. I mean, the silver lining though is that I think if you you can still get a very a decent prediction, at least in my experience, if you take the population parameters that you learned at inference time and then have a more informed prior for your new members of the existing groups. So you can still get, even though mathematically it's not the best that you could have, because the best would be to do what we just talked about, that's a practical solution that's not too hard, and that at least is accessible to most people right now. So yeah, don't despair, folks. Even if we can't do that right now, you still can have decent predictions for
new members of existing groups without being completely doomed.
Yeah, so actually on that point, like the transform, because I went through, another way that possibly I think that you could do that is if you unconstrain, like if you do the unconstraining transform of your estimated zero-sum vector. And so now you'll have like k minus 1 elements, right? And then you add a new one. Well, like you just randomly draw a normal 0, 1 or whatever it is that your kind of prior on the unconstrained scale would be. And then you just go back and in the case, I think for us, it would be you just add that whatever you drew from the normal 0, 1 divided by the square root of like k plus 1 times k plus 2. And then the last element would be the minus of that.
But I think that's still missing something, because we still need to kind of, then we are adding that variance in a sense. So kind of we were saying the variance from the sample mean, we are adding it back there. But that variance is kind of absorbed in the intercept term now.
So yeah, this would
so
just
we kind
be
of actually need to take out the variance out of the intercept term. So we can't just add the variance, we also need to remove it at the other end, right?
Yeah, but there might be a way where you can use like I don't know, that unconstraining transform, and then it would be much simpler in my mind, because it's just like, oh, I just have this function, it would apply all the stuff, and then it would come out. Anyway, I'd have to think about it more.
Yeah, story of my models.